Let's take a directional derivative using the limit definition in example 11.2. So remember, the directional derivative is the slope of your function when it's restricted to a hyperplane that is in the correct direction, right? So your partial derivatives are your directional derivatives in the direction of 0, 1, and 1, 0, right? In the direction of x and in the direction of y. Your directional derivative could be in any direction that you want, though. So our function here is x squared plus xy. Let's copy that down. And I want to find the slope of this function, or the directional derivative, at the point 1, 2 in the direction of 1 over square root 2 in the x and 1 over square root 2 in the j, or in the y. I don't know why I said it like that. All right. So we want to evaluate the slope of this function at the point 1, 2. And we want our hyperplane to intersect our function parallel to the vector u, which is 1 over square root 2, 1 over square root 2. So it's important that this is a unit vector, right? Because if you define slope, you don't define it as 3 over 2, as in you move 2 units and then you go up 3. It's always over 1, right? If your slope was 3 halves, then how you would interpret this is you move over 1 unit, then you go up 3 halves of a unit, right? So we need to make sure that we move 1 unit distance in our domain. So I need to make sure that this unit vector that I'm traveling along is indeed a unit vector. And take a minute, pause the video, make sure that the norm is 1. All right, this is a unit vector. So our limit definition of the directional derivative of our function at the point 1, 2 in the direction of u is defined as the limit as s goes to 0, where we'll define s here in a minute, the function at the initial point, and now I move in the direction of u, s amount, right? S tells me the length that I travel along that unit vector. So I'll take 1 and add s over square root 2, because that's the direction of my x component. I'll take 2 and add s over square root 2, because that's the direction of my y component, right? And s is the number that travels me along that direction. And our goal is to send s to 0, i.e. we're shrinking the distance that we travel. It's really the exact same thing as your regular limit definition of a derivative, except now we're not specifying the direction, or rather, we can go in any direction, right? So that's your function at a little bit past your point. You'll subtract off your function at the point, just like we do in our regular derivative, and then we'll divide by the distance that we traveled, or s. All right, here it's just chasing a bunch of algebra. So we have the limit as s is going to get sent to 0. If I evaluate my function at 1 plus s over root 2 and 2 plus s over root 2, then I believe you should get 1 plus 2s over root 2 plus s squared over 2 from that x squared, right? Because this is your x. All right, now plus the xy, so I believe you're going to get plus a 2 plus 3s over root 2 plus s squared over 2. And now we need to subtract off our function value at 1, 2. So if you place x is 1, y is 2 into your function, I believe you get a 3. All right. Simplifying the algebra, we end up at 5s over root 2 plus s squared all over s, which if we take the limit as s goes to 0, we pull out the s from the numerator and we are left with a 5 over a root 2. So the slope of this function in that direction is 5 over root 2, meaning that if I travel in fact, So this is a bird's eye view of the function, right? There's my x-axis, there's my y-axis, that's my domain, it's 2 dimensions. If I travel in that direction, that exactly bisects my x and my y plane, because these have the same norm. So as I travel in this direction, my function is increasing at a rate of 5/√2 every unit movement in that direction, at least at this point.